Okay, let's do another example of a single sample t-test. Okay, again, I'm going to use examples with small samples size because we're going to do this by hand. The procedures that we use in these t-tests are the same procedures you would use if you had a sample size of 127 or a sample size of 42 or whatever the sample size is. I just want to make this manageable for us. So let's suppose this. We know, and this is going to be our given, that the average waiting time for ER for someone to be seen at a particular ER is 24 minutes. So let's do that as our given, 24 minutes, okay? And perhaps the staff at the hospital and the CEO are interested in trying to decrease that time because 24 minutes is a long time, especially if you have an emergency. And so maybe they're inspired by what you would see at an airport, check-in facility where you have a kiosk where the patient might be able to enter their own vital signs with the equipment there and also enter the information about why they are in the ER to be seen. And so then the staff, instead of doing that, can focus on servicing, seeing the patients. And so we're going to put up this kiosk. And then let's look at the next 10 patients that come in, and we'll see how long that they had to wait to, to be seen at the ER room. Now, we can easily, let's do this. Let's set up our hypotheses first, right? So the null would say that the mean for the kiosk population, of which we're assuming the next 10 patients will be a sample of, right? So that's going to be our sampling from this population, the kiosk population. And we're going to say that that's going to be the same as what we see normally in the ER, okay? And of course, we can replace that with a value if we want to. The kiosk is going to be, the waiting time is going to be 24 minutes, just like we saw before. The alternative is that the kiosk, after we put the kiosk in, we're going to see something different than the normal waiting time. And that is, we're going to see something different than 24 minutes. Okay? Now, I haven't given you a sigma here, and so because you're missing that information, in a way you should know that, well, we can't do a z-score because we don't have the sigma, that is the normal variability. And I'm still going to do my alpha level here. My alpha level will be 0.05. I'm doing that to try to reduce the risk of making a type 1 error. But I'm going to need to get a critical t value now instead of a critical z value. And let's suppose that we have a sample of 10 people, right? The next 10 patients, we're going to see what their waiting time is. So the degrees of freedom here will be 9, okay? It's n minus 1 for our degrees of freedom. If we go to the book and we look here, we see that the critical value is 2.262. It's going to be plus or minus 2.262. Now remember, this is like our z-score of plus or minus 1.96, right? It's the equivalent cutoff for the extreme 5%. A t distribution is more variable than a z, and so we need to move the critical t-value outward a little bit, okay, to 2.262. It's still around 2, and we will talk about that in a little bit. Since this is a ratio, right, the top is the difference between the groups, the bottom is the variability. We want the top to be about twice as big as the bottom. It actually needs to be a little bit more. But the concept is the difference has to be about twice the variability for us to get a significant t-value or a significant z-value. The top has to be twice as different, twice the size as the bottom. But we're not going to use this z of 1.96. We are going to use this for our critical value. Okay? So let me give you the numbers. 21 minutes, 13 minutes, 26 minutes, 29 minutes, 12 minutes, and 20 minutes, and 25, 21, 28, and 24. Now you might notice there's lots of variability there. There are some numbers, 21, 13, 21, 12, that are below this, but there are also some that are above it, so we're going to have to see what goes on here. Now, I'm going to use, I'm going to go the other direction now, this time around. That is, I'm going to show you the t-test formula first, and then we will fill in, right? So there's the t-test formula. This is our sample mean, so we'll get the mean for these numbers. This is what we normally see the waiting time. We're going to get that from here. I mean, it's 24 is mu, but I know that mu sub m is the same as mu, okay? So if I calculate the mean for this group, and I want you to do that for sure, it comes out to be 22.10. So it is less than 24. When I compare it to 24, this is less. We're going to have a t-value that's negative, right? 22.1 is below the mean of 24. I'm going to get my S sub m and put it in that value. And here's what I'm going to do. I know S sub m is equal to S divided by the square root of n. This is my central limit theorem step, right? And I know what n is. N is 10, so I have that already. I need to get S. Well, S is sum of squares divided by degrees of freedom, or n minus 1. We're going to take the square root here, okay? So this is, S is our guess. S is our guess for sigma. S is our guess for sigma. Once I have my guess, then I need to do, right, so this is a two-step process. Make your guess for sigma, then do your central limit theorem to go from sigma to the standard error, okay? That's what we need to do there. And I'm going to give this some more room here, okay? By the way, if you're following me, and I hope you are, I do want to take the time to give you a pat on the back. I mean, this is pretty awesome because it wasn't that long ago where you had no idea what statistics was about. You wouldn't know how to do it at all. Now you're able to follow me, I hope. Okay, so our sum of squares is this. Okay, get my sum of squares for this group of numbers. So the sum of the x squared values, and you should probably pause the video and do these computations, okay? And then come back, because I'm just going to put the numbers in. This is 5149 minus 221 squared divided by 10. Okay? When you do those calculations, you come up with a sum of squares value of, I hope, 264.9. Now plug that into here, okay? 264.9 divided by 9, now, degrees of freedom. Take the square root, okay? So, 264.9 divided by 9, take the square root, 5.42. Oh, let's make it 4.3, since it's 425 something, 4.3. Once we have this, now I can go right to here, right? So this is 5.43 divided by the square root of 10, okay? And so let's do that, 5.43 divided by 3.16. So this is 1.72, okay? 22.1 minus 24 equals, gives me negative value, right? Divided by 1.72. Oops. 22.4. 22.1 minus 24 divided by 1.72. So our t-value here is negative 1.10. Negative 1.10. Okay? Now, just like I did before, when I calculated my z-score, I compared it to my critical. Of course, that always stayed the same at z of 1.96. Here we need to take our t-value, compare it to here, and one more time, folks, because I can't do this every time, right? So here's what we're looking at. Critical t, 2.262, negative 2.262, okay? These are our critical t values. It defines the extreme 5%. Our t value here, this would be 0, because it would be the mean. Our t value is somewhere here, 1.10. This is expected for the normal wait times. Okay, so in this case, step 4, we're going to fail to reject the null. We're going to fail to reject the null then in this case. Okay? How are we going to write that as a conclusion? Okay? So number 5 is it appears that having patients use the kiosk for entry of information. I mean, this can be said in a number of different ways. Kiosk for entry of information does not affect, that's an A there, does not affect wait time to be seen in the ER. Something like that. I always make it tentative because it's a probability statement. This you can work with, and you can always revise and try to make it better or whatever. I'm going to justify this statement by saying T with 9 degrees of freedom is equal to minus 1.10, semicolon. Now in this case, I'm going to say P greater than 0.05, close paren, period. What this is saying is the probability that the null hypothesis is true is greater than 5%, okay? And so if the probability of the null being true is greater than 5%, then I'm not going to reject it. And so I'm going to conclude that, installation of the kiosk was not effective in reducing wait times. Okay? And that's that. That's another example of our single sample t-test. I do want to point out a couple of conceptual things about the t-test and the z-score. I mean, here's our z-score. In fact, I'm going to show you the z-score for single scores. Right? This is where it all started. But then we said, well, let's do samples. So instead of doing a single score comparing it to the mean, I'm going to do a sample mean, compare that to mean of all the samples, divided by the standard deviation of all the samples, okay? The t-test is of the same format. In fact, it is so close, there's really only one difference, and that is, see that? There's really only one difference, and that is the S instead of the sigma, because we're going to use S as our guess for sigma, right? S is our guess for sigma, and then S sub m is our central limit theorem step, okay? Get our guess for sigma, get central limit theorem, then put it in there, okay? But I want you to notice the form of these ratios, okay? This is a difference over variability. This is a difference over variability. This is a difference over variability. It's all the same form. This is when you have a single score and you know sigma and mu. This is when you have a mean of a sample and you know sigma and mu. This is when you have a mean of a sample and you know mu, but you need to make a guess about the sigma and then do your central limit theorem, okay? It's all the same form. Now, our critical value here is 1.96. Our critical value here was 1.96. Because we know sigma, we have one distribution. This will change depending on the degrees of freedom. But, I want you to pay attention to these values. They're all about 2. Now, we're going to be careful and much more specific with, when we do the work in this class. But in general, we're looking for something greater than 2 from these tools. And the beauty part of this is the ratio has to be 2 or greater, okay? But that means that maybe the top could be 4 and the bottom could be, 1.5. That would certainly give us something more than 2. Or the top could be 100 and the bottom could be 40. That would give us more than 2. Or the top could be 0.3 and the bottom could be 0.1, and that would give us more than 2. right? Or the top could be 501 and the bottom could be 100, and that would give us more than 2. The point here is, I don't care what the difference is. The difference could be as low as this or as high as this, and it's going to be significant. It's the relationship, folks, the relationship between the top and the bottom, not any kind of absolute thing. I've seen so many times from people that should know better, somebody will say something like, well, the difference up here, the difference between the mean and what I expected was 200. So that must be statistically significant, right? If this top is 200, wow, that's a big difference. Well, 200 isn't a big difference if the variability is 500, right? That would give us a ratio of 0.40. That's not big enough, okay? So you're not just looking at the difference. The difference of 200 means nothing if the variability is 500. A difference of 200 means a lot if the variability is 50. That's huge. Same difference compared to variability. We talked about this when we talked about z-scores. Also, somebody could say, oh, there's only a 4-point difference here, so that's probably not going to be statistically significant. And I'm like, well, a 4-point difference, if the variability is 1, then a 4-point difference is huge. A 4-point difference means nothing if the variability is 12. Okay? The point here is that we're not looking at just the difference. Just like we started in chapter 5 here. We're not looking at what your score is and how, first we need to compare it to the mean. But if you're 10 points above the mean, but the standard deviation, the average deviation is 20, then 10 points above the mean doesn't mean as much as if you're 10 points above the mean and the standard deviation is 3. Wow, that means you're far out. You see, we did it with single scores. We're going to do the same thing with samples. We're going to do the same thing with samples when we're making our guess about variability. It's the relationship of the difference to the variability, the relationship of the difference to the variability that matters, not just the magnitude of the difference. Everybody with me? A 100-point difference doesn't mean anything if the variability is 200. That would be our t value or our z value. Difference of 100 means a lot if the variability is 25. Oops. Okay. I kept 100 the same. We talked about this before in the very basic, building blocks of z-scores. Now we're kicking it up to samples. We're using samples because we know samples are going to be more representative of population in general than any given single score. Samples are more representative. And then here, same logic. We just need to now make our guesses about sigma. Okay? Please don't forget the conceptual while you're doing the computational. As a teacher, I'm not going to choose one or the other. They are both important. You're doing this stuff because you understand these concepts. You're doing this stuff because you understand the concepts. And just like on the first exam, maybe the second exam would even be, or third exam would even be more conceptual, but I'm still going to have you do computational and conceptual. Okay? It absolutely goes together. It doesn't make any sense to extract one from the other. Okay, so it's a little bit shorter of a video because I know I went a little bit longer on some previous ones, and you also took some time, I hope. Make sure you can do the sum of squares. Make sure that you can do that, and then plug in the rest. Okay? as you go along. Let me know if you have any questions.